Okay, so hello everyone, my name is John Xu. I'm going to be presenting on procedure generation in 2D Metroidvania games with answer set programming. So the idea behind this is that I should first introduce answer set programming. It is not something that is extremely conventional, I would say, that people will usually use in conjunction with Metroidvania games. So the idea behind this is that it is a form of declarative programming that is used to solve non-deterministic polynomial time hard problems. So I won't get into the specific computational complexity of answer set programming, but the idea is that it is basically it is an algorithm that searches for solutions that satisfy certain constraints that we give it. One, I would say, extremely famous example of answer set programming is the n-queens problem. I don't know if anyone plays chess here, but the idea is that basically you're given a certain amount of queens that you want to place on the chessboard, and you want none of the queens to really intersect each other, basically not be in each other's attack range. And as you can see, right, this is a very famous example where you can certainly verify that the solution is correct extremely easily, but you kind of start to have a hard time when you try to find a solution where it actually works. And of course, there's the sense that there's multiple solutions which will come in handy, right, when we're talking about procedure generation in any sort of video game. So, sorry, slides is a little slow. So answer set programming has a very unique syntaxing. Oh, sorry, that's the next slide. Answer set programming has very unique syntaxing. It is definitely not very conventional. We end every line with a period, and our lines are kind of usually one of these basically conditions or choices. The most, I would say, common one is facts, where you have a header, a neck, and a body. So this little symbol here is a neck. So basically, what the body is basically a set of conditions. And then the neck makes sure that for every time this condition is satisfied, the header is executed. So it is kind of I would say, a mix between an if statement and a for loop, if I really wanted to get into it. But we also have negations, which are kind of like a variation of what we define as a fact. So we say that for every time the body is true, the condition is true in the body, that there will be no header. So basically, there will be no action there, so it does not exist, right? So these two kind of go together as they really define what is what, right? The whole idea of answer set programming is that we're trying to kind of program a set of answers that satisfy the logic that we have restrained it to be. So in this case, these two play in very handy when we're talking about kind of trying to logic things out. And then we have a little less common, but choices and constraints. These two also kind of go together in the sense that you basically you can define kind of, I'd say, a collection of different choices, and each choice is called an atom. Sorry, excuse me. And basically, the idea is that the program can choose a permutation of the choices they are given. You can constrain the permutation that the program chooses from. So in this case, I restricted the constraint from 1 to 2, which means that you can have at least, the program can pick at least one choice, or at most 2 choices. It cannot be 3 choices, and it cannot be no choices. And we also have range and conditional iteration, which also goes together. Kind of in the sense that range basically provides all the choices from your start to the end. So you can do like 1 to, I don't know, like n, 1 to x, something, some kind of variable that you can define. And conditional iteration basically is sort of like a for loop in the sense that it basically says for each x value and y value, there's going to be a coordinate of x comma y. So this is kind of the idea, similar to what we have about with facts, but this can be used in conjunction with the syntacting of facts to produce some other complex results. And this will come in handy. Definitely this coordinate system logic will come in handy when we're talking about procedural generation that involves set tiles, set blocks in different parts of the level. So moving on a little, Metroidvania games, right? We have to kind of define what Metroidvania games are, right? That's the whole idea, is that this is kind of the careful, I would say, marriage between Metroidvania games and answer-set programming. So Metroidvania games usually come in, I would say, a lot of flavors, a lot of forms, but the important part about kind of using answer-set programming with Metroidvania game, I guess the relevant part of this is that Metroidvania games involve a very strategic placement of keys and gates. So you want to always make sure that the keys come before the gates. And I'll kind of explain what that means there. So the idea is that basically you want a very, very, I would say, maybe not straightforward, but definitely an easy and accessible way to pass through the entire level without getting the player stuck. And when you're dealing with sometimes levels that are very big, like industry level kind of games that I've shown here, it is sometimes hard to keep track of everything, and you may end up really trying to, I would say, like going back and trying to fix some parts of the level. So it is definitely a challenge to put keys before gates. So kind of going a little more specific into the key/gate mechanism, this is kind of one of the, I would say, focus points of this research. A key and gate mechanism is just any mechanism where you have a key, which is anything the player of the Metroidvania game can use and pick up to help the player get through an obstacle, which is preferably later on in the level, so that the player can get across that obstacle, right? There's different types of obstacles. You can have a direct wall, right? Like an actual door and an actual key, right? That's the most straightforward way where you can represent a key and gate, right? In that context, if you think about it, you don't want to lock the key behind the gate. Otherwise, the player will never get behind the gate because there is no key to unlock the gate, right? So this is just one kind of example of kind of a graph which shows a level and specifically like how its keys and gates are arranged. You can see that the keys, right? This is like a bow and arrow, I would say, key, right? Represented with the diamond shape, always comes before the square shape counterpart. So that goes for the blue key and the blue gate, the red key and the red gate. So these are some just examples of that, and I will get into more specific details into how we apply kind of key and gate mechanisms in like a video game that we kind of develop in conjunction with this methodology. So this is kind of another example, a lava gate and a key, right? If we just kind of strip this down to the very minimum, the red kind of circle is the key, and then the gate is whatever lava is here. So the kind of idea is that if the player were to come across lava, the player will start to burn, and that is not good, right? The player will not be able to progress past this point. So we need the key for the player to kind of overcome this in any sort of way. It can be like you can, I don't know, walk on lava or like not burn in lava. There's just different features. And that's not really, I would say, specifically relevant to what we're doing. We're just making sure that the key exists, and the actual implementation can be up to the actual game developer. So again, right, since this is such a unique, I would say, style of doing things, and I'll get into a little some examples of some more mainstream ways of doing procedure generation, right? We have so kind of, I wanted to just list out some of the tools that we used, right, to achieve this unique kind of connection between two really traditionally separate things. So answer set programming in logic, right? ANS Prolog is what we use to actually do the programming part of the answer set programming. It's basically the language we use to actually do answer set programming. And we plug whatever code that we wrote in ANS Prolog, right, into a solver. And there's many solvers, but we're using Klingo in this case. And so basically we're just plugging Klingo, plugging the ASP into the Klingo, and then that will give us certain outputs we hope to desire based on the restrictions we place. These outputs will be used in the Unity 2D engine, which is just, and in conjunction with Visual Studio. So these kind of two bottom bullet points, they're just, I would say, a very conventional way of actually doing usually just small scale like video game development. And we just use this as kind of like almost a front to demonstrate the methodology that we have established with answer set programming. So this is just kind of putting it into the Unity 2D engine using like C# scripts we've used in Visual Studio to kind of build out the actual level that is dictated by the solution of the Klingo. That kind of resolves itself, and we actually get pretty nice level generation. All right, so I talked about kind of how we would try to divide or try to generate the level, right? The fact that the scripts would kind of build this out for us. So early kind of research showed us that with kind of increasing room size, actually, sorry, I should explain kind of the hierarchy first. So the idea is to build a level, right? That is the biggest kind of hierarchy, like I would say, status here. So this is the biggest thing that we're trying to build, but we've really devised, I think, more of a divide and conquer strategy where we split the generation into much more smaller pieces in order to generate each more effectively. So we have different rooms in the levels. They're equally sized, and there's just a certain amount of them that are equally divided out from the level. And these are really just arbitrary definitions based on what we define as a room, like basically the room size, right? So if I have a 20 by 20 room, which refers to the amount of tiles in a room, which I'll explain a little later, and then you'll have like a 6 by 6 like level, then you have 6 by 6 20 by 20 levels, if that makes any sense. So we want to really minimize the runtime, right? That's why we're dividing so kind of into more and more minuscule parts, so that we don't struggle with a lot of, I guess, like long solve time. And yeah, so then we get onto the platforms, which are certain groups of tiles, which I'll explain a little later, in the platform. And they're related to how we determine the directionality in the room. I'll have a separate slide for this a little later on in the methodology section, since this is something a little more specific. And then the tiles are just the most fundamental unit in our level generation. So we can view them as just a pixel, basically. And groups of pixels make the shape, determine the shape of the eventual level generation. So that's kind of the idea. So I also talked about kind of the idea of the like more mainstream ways of generating and generating kind of procedurally level generation usually. And so I don't know if I guess anyone who's very familiarized with Perlin Noise, but is, I would say, much more common to use Perlin Noise. It has its downsides, but it also has its very clear kind of upsides. So with Perlin Noise, the idea is kind of you stack layers of waves that have different differing amounts of frequencies and amplitudes that are determined by things like lacunarity and persistence, which I won't get into the detail here, but the idea is that you stack layers of waves on top of each other to determine noise map, and you can kind of map that noise map with different values corresponding to different kind of generation, different tiles or to different pixels, and you get yourself a pretty nice looking level. So since it's very easy to kind of, I would say, calculate a noise map, a Perlin noise map, and use the Perlin noise to map out a level, it is much more simpler to generate something in this case, but it is much harder to, I would say, to really verify if this level is actually passable by any player, right? So we have no guarantee that the player can travel from any point A to point B. So this is the problem with Perlin noise, where we don't have directionality, right? And this is why it takes a lot less, because what it's doing is just very mathematical and very straightforward, right? There's no like really like hard determination of where we're going. Yeah. So this is kind of the idea behind Perlin noise, and this is kind of something that our kind of solution proposes to counteract and solve. But as you can see later on, there are a few problems with our solution later in the results section. So let's get into the actual methodology of how the how answer set programming works in conjunction with 2D Metroidvania games, because I've been kind of hinting towards this, and I want to get to that. So this is kind of the idea behind this is just a general graph behind the level generation that we're dealing with. This might not make too much sense at first. This is kind of to just give you a general idea of what we're dealing with. Even though it doesn't look like two steps, I usually relegate this to a pretty I wouldn't say straightforward, but definitely two-step process, two general steps, I should say, in order to generate generate the final product, which is a level inside the Unity game engine. So what's important here is that we want to determine directionality as soon as we can, right? Because that is the whole point of kind of how this level is going to work, right? Only if we know which direction the player can go in a certain room can we determine if the player can traverse throughout the entire level. So the traversability of rooms, the directionality of each room will determine which way the player can go and if the player can traverse to the end of the level. So that's kind of something very important that we have to take care of very early on. So to determine directionality, we have to make sure that the player movement is accounted for. So I'll have a little more demonstration of how this works in the next slide, but as you can see that the player can move any amount of space, and that is not really an issue, but like if the player is on the ground, right? The player can move any units left and units right. That is fine with us. The player can also jump up 3 tiles, no more than 3 tiles. If the player if there's more than 3 tiles, that means the player cannot jump back. And sometimes it's helpful to do that to kind of limit where the player is going. So and also the player can kind of move diagonally in the air, right? Because you can kind of, it's basically the idea that you're moving left or right in the air, right? So this is kind of mimicking this, which which is kind of a little naive, but it works for the most time. And it also works for falling down and falling diagonally down if you're pressing left or right, right? So the idea is that basically you are kind of mimicking the movements of the player and where the player can go. And the player is 2 tiles tall, right? We talked about tiles a little before, right? So we just have to make sure the player, that if you want a path, right, for the player to pass through, you must make that path at least 2 tiles tall for the player to actually fit through. So this is kind of a little better demonstration of what we're dealing with. As you can see, the player jumps up 3 tiles, and most 3 tiles, we see the diagonal kind of movement that I was talking about before, and we see just regular left and right on the ground, right? So these are kind of the movements of the player, and that will come in handy when we're determining the directionality of the rooms. And we get finally a little more about platforms, which I didn't mention earlier. So how the platforms are defined are all the ground tiles, so the tiles which the player can walk on, all the ground tiles where basically that is connected by the player's kind of movement. So basically, I would say like one obvious example is how we divide the left and right platforms in this case. So there can be, as I said, multiple tiles in a room. This is a room, right? So the fact that this is 4 blocks tall, 4 tiles tall, the player cannot jump over that. So they remain separate, right? In the sense that left can't reach right, but right can drop down to left. So this is why we define them as distinctly separately 2 platforms, right? And basically, due to these platforms, right, we can see, like I kind of said before, right? Left cannot reach right, but right can reach left. That is directionality, right? You can move right, you cannot move to the right, but you can move to the left, right? So this is directionality kind of defined. And we also have middle the middle platform, which is kind of like its own thing, but as you can see, like all the dots, right, represent the player's kind of path. So the player can be on top of the middle, but then it by itself is not connected to the left or the right, so it is considered an individual platform. Now there can obviously be more than like 3 platforms per room, and we won't probably be able to call left, right, or middle. This is just kind of a demonstration to kind of show like what kind of we're dealing with. So yeah, so with platforms, we're able to determine directionality. I think this is the most important part of how we can guarantee traversability throughout a level. It is with platforms, right? The idea that you are able to reach one point, but from one end of the room to another end of the room, but not the other way around. So this limits and determines directionality, which can, like I said before, be kind of used later on to figure out the entire traversability of the level. So now we kind of get to actually using this directionality, right? So we the first step kind of, well, I guess they're all part of the first step. That's why I said it's first 2 general steps, because they're not very straightforward 2 steps. So we're using this kind of directionality that we've kind of determined, we are able to basically restrict, basically graph out every room and every room's relationship to each other. Some rooms can connect to other rooms, and other rooms may not be able to connect back to these same rooms. So we have bidirectional, right? For example, 3 to 4. So room 3 to room 4 is something that you can do, and you can also travel from room 4 back to room 3. So they're represented using a bidirectional arrow, therefore they are bidirectional, right? So in this case, we see like how the rooms connect, right? We have 1 direction arrows, which means that we can get from 3 to 13, but not back. And there can be no arrows at all, but like, for example, between 2 and 3, right? And then there's no way to reach 2 and 3 because they're physically blocked off from each other. It's not like there's a gate or anything. It's just that there's regular tiles that are preventing movement. I would also probably want to explain what the colors mean. So the colors correspond to different types of key/gate mechanisms. Like I kind of showed, red represents lava. I have water, which represents, well, blue, which represents water, and then the yellow represents normal doors in the levels that you're supposed to unlock with keys. And the rhombus shapes represent the keys, and the square shapes represent the gates themselves. So we want to kind of make sure that that is the case when we're dealing with kind of how we represent it. So the graphic contains the information about how the rooms connect and how the rooms, like the kind of the type of room that we're dealing with. The light green room, there's only one each scene that represents the start room where the player starts in the scene, and there's always a guaranteed path from the start to the end, which is this kind of 2x2 room structure here, which I just dubbed the boss room, which is basically the end. So there's always guarantee that we can reach that place. All right. Okay. So now we kind of move on to the second step. I would say the first thing we want to know is that kind of what we're dealing with is in the second step. So the second step of the procedure is that we're trying to kind of actually lay out each and every tile of the room. Right? We're trying to lay out the fact that basically well, right, because up to this point, we only have how the rooms connect, what kind of types of room there are, but the rooms themselves aren't there. The rooms themselves aren't really being generated in any sort of game engine, no, nothing at all. There's just at most a graph that we can deal with, right? So we want to actually build out each and every level. And so, like I said, right, we're trying to do this divide and conquer strategy, right? So we're trying to divide the levels into rooms. So we generate room by room. And basically, what we're dealing with is that basically we want to make sure that the directionality that we've determined before is satisfied, but also that the path fit the player's kind of description, fit the player's kind of, specifically I'm talking about height, right? Like we mentioned before, if we want a path to open for the player, the path must be at least 2 tiles high because that's the restriction on the player. And so that is one thing that we want to make sure to determine, right? To prevent from really kind of going out of hand. And I would say that this step alone is, I would say, really actually enough to generate a level, but it is definitely not the best level, right? Since we're dealing with room geometry, one room by one room, right? We have no real way to make sure that the rooms actually kind of communicate with each other, right? Even though we have directionality, what ends up happening is that you might have rooms that look like they're extremely separate, right? They don't look like they're part of the same kind of level, right? Because what we're dealing with is that the answer set programming is only kind of worried about I would say that's particular room when we're generating that room, right? So we're not considering any of its neighbors. So what we end up doing is that we copy over the room geometry from all the neighboring rooms. So for example, if this is on the right side, the room we want to build, I think I have, if room 2 is the room that we want to build, we copy over the right edge of the room 1, since the room 1 is the left neighbor of room 2, over to room 2 side. So basically what that means is basically the edge geometry is just like the edge kind of one tile kind of strip that we get from room 1, and we just directly copy that, shift that 1 unit to the right, and we get the kind of starting structure for room 2. And we pass this kind of notion, this kind of preset into the answer set programming, and the answer set programming solves based on the knowledge that the room geometry has already been mirrored. So we can be assured that the room geometry will match, and therefore we'll have a very smooth transition between rooms, but also that directionality is considered. But sometimes it doesn't do that. So which kind of comes into play when we're talking about the iterative conflict resolution algorithm. It is designed to resolve the conflicts of basically when directionality goes against kind of the room mirroring room geometry. So since we can't really get rid of the room that we're trying to build, right? What we end up doing is that we end up kind of changing its neighbors around to match the room that we're trying to build. So we're going to build this room right here, as you can see in a little bit. We're going to build this room right here, right? And with this room in mind, right? With this top right corner room in mind. But as you can see, what we meant to have a kind of direction is hindered, right? It is not really copied over, right? What we kind of meant to happen did not happen, right? Because we tried to copy over the mirror geometry because we're kind of a little greedy with trying to make the rooms look nice. So this is a problem, right? We can't have this problem. So what we do is that we end up, the eventual result is that we had different variations of how we tried to do this, but what we ended up doing is that we basically generated all the permutations of rooms from smallest to largest, and basically just went from smallest to largest permutation of neighboring rooms and removed each permutation to see if that is causing the causing the unsatisfiability in the room that we're trying to build, right? In this case, it's just this one room. So right, as you can see, the directionality doesn't match the arrows. There's a few tiles here that block the player from moving. So what ends up happening is that we change this room and only this room. And as you can see, we're trying to build this room, but we removed this room, right? Because it's one of the neighboring rooms that we're trying to build. And that is, in this case, what is causing the iterative conflict. Sorry, the conflict. And we kind of fix around that by regenerating the room to match what we had before. So this is kind of more visualizing what we're dealing with. Of course, if the room is on the edge, like we kind of saw before, there will be no kind of right side or left side. That's an edge case. But basically the idea is that you will have all the neighboring rooms kind of determined here, and a permutation of any of these must be kind of generated. And basically each permutation is tested to see if it is the problem that is causing it. Because sometimes there can be multiple neighboring rooms that cause the room that we're trying to build to fail. So we want to get kind of the entire set that we're trying to deal with. So this is the kind of idea behind the iterative conflict resolution algorithm. So this is kind of what we end up kind of seeing. This is just the actual level doesn't run this fast, but this is just kind of a GIF or GIF, however you would like to pronounce it, of what kind of we're dealing with, right? As you can see, some rooms are being removed, regenerated, right? Because we find out that it is not satisfiable, right? So yeah, it happens quite a lot. So it is definitely an important algorithm to have. And as you can see, after this whole algorithm is through, with each and every room that was presented back in the graph, right? Which kind of is like a blueprint, we get a level, right? And starts to work. But this is kind of the idea. So, well, we have a level. So what did we find? What are the results we found? So the first thing we tested, and the most, I think, I would say maybe not the most important thing, but definitely a thing that we tested for is solve time. So how long did it take the answer set programming to solve certain problems? Since the whole idea is that it takes a long time to actually find a solution that satisfies the conditions. And considering that the more conditions you give to answer set programming, the harder it is to solve for a solution. And we're dealing with a pretty, like, I would say, large scale project. There's going to be a lot of restrictions, so it's going to take a lot of time, right? As you can see, some levels take a pretty long time to generate, I would say. This is definitely one of the downsides of our methodology. And it is definitely something that we have to kind of optimize for. But we kind of trade that solve time for traversability, which I'll explain a little later. But first, right, kind of what is the graph kind of showing? So the idea is that we have different passageway types for the rooms. So the rooms can basically have different kind of ways that it, well, basically the directionality in the local room, basically. So if, for example, this is basically that you can enter and exit right or left, or like you can go left and right, and then you can go up and down, and so on and so on. And it is separated between bidirectional and directional, because we just want this very clear separation between what is what. Some of these are not necessarily bi-directional. This is like all directions, but it kind of gets the idea across, right? But only look in the arrows, like you don't really see how you were able to like achieve some of these. Like, for example, like how can you make a room that only allows the player to go up? Now, we can do usually, right? Kind of logically think about this is not really possible, right? Because if you're able to climb up something, then you're probably able to fall down it, right? But the thing with kind of the beauty with answer set programming is that it is able to figure out that, because we know that the restriction of the player's path is 2 tiles, right? That I've been mentioned that a few times already. So these are some of the passage percent. How can we achieve directionally up? So this is an example of room where you can achieve directionally up. It is definitely takes a long time for the answer set programming to find, but it is definitely there. So I kind of just kind of graph this out. This wasn't this is just a demonstration to show a possible way that the answer set programming could achieve a directionally up level. So this is the up part of the directionally up, right? As you can see, if you can go up from here, move and move, and you, of course, you can make this jump and then continue and then kind of fall down from here. You're able to, if you fall down to this pit, you can still jump up and then move on, and then move up to move upwards, right? But if you try to go the other way, what happens is you move down, right? You try to jump, but you get blocked by this tile here, and you kind of fall into the pit, but this pit is 4 blocks tall. So you have no idea of getting out of the pit, but you can still go backwards, right? It's kind of just preventing you from going down. So this is how you achieve a directionally up level, which is kind of very interesting to see. Definitely something that you wouldn't usually expect. But then this is another just type that kind of mentioned all direction rooms, right? That you can go all 4 ways, right? Within the room. So this is just a demonstration of that, a visualization, because it does tend to get a little harder to visualize. So now we talk about traversability, which I think is the most important. So this is an ASCII representation of the entire level. Basically, the X's represent the tiles. We have the R's, which I don't know if you can see very clearly, they represent the gates. And we have the keys somewhere along the lines of the path of the player, which are represented by the ampersand symbol. And then, sorry, not the ampersand, just the @ symbol. And basically, we start from a certain point, and then we basically plug all our levels, all the ASCII representations of all the levels that we've generated into a pathfinder, and it basically tries to find a path through the ASCII representation, the level. And we give restrictions like you can't pass the gate, but if you have a key, you can pass through the gate. So basically, the only way that the pathfinder could pass through the gate is if the player if the pathfinder received the key before the gate, right? So you pass through the gate, and then we climb and climb up, and we can reach the end. The end in this case is over here, right? So and this is a little better representation of what we're dealing with, right? This kind of merges the graph with the actual level. So this is the the light green circle, right? That I was talking about, the starting room. So the player definitely starts somewhere inside this room. And then we go down, right? And then we kind of pass through. And these are all the rooms that we define as locked behind a gate, in this case, the water, right? I just have water as an arbitrary gate. You can imagine this as anything else, but basically, you want to go down and then reach this point eventually, because there's no actual real other way to go. So you reach this point, and then you have the key here, which you can pick up, and that allows you, right? Key before gate. That is always determined. Keys before gates, right? You pick up the keys, and then you're able to traverse the water, all right, and then you kind of you're able to pass the gate, right? And that is nice, and that means that we're able to get through the final kind of level and get to the end. So we pass through, we kind of traverse, right? This is all determined by the rules that we've set for where the player can and cannot go. So the player goes up and up and up and up, and then we meet another water gate, but luckily we have a water key, right? So we just pass through the gate with the key that we had before, and we reach the end level, and I have just a different colored like player model as like the boss, just as a representation. But basically you're able to pass through the gate to reach the end, and that is guaranteed, right? The start to the end, right? That is a guarantee. So yeah. And then this is kind of the final product, I would say. It's kind of dark because of how the lighting works in the level, but as you can see, this is a mix between enemy gates and lava gates. So enemy gates in my case is basically just, you cannot really see them very well, but you can kind of identify them by their green kind of health bar right here. And the idea is that you would want to have the keys to come before fighting the enemies. Otherwise, you don't have any key, right? In this case, it is just like I don't know, like there can be multiple things, but in this case, it's just basically a regular video game like weapon, and you can use that to fight any sort of enemy, right? Some kind of offensive thing you can try to fight the enemy with, and only with the key can you pass through the kind of part that is guarded by the enemy, which is here, and only with, right, the gate for the lava, which is red, can you pass through the lava themselves. So that is kind of the idea of that we're dealing with. And the lights, if anyone is curious, is just kind of randomly generated. They're not specifically ANSYS programmed because we kind of just place the lights based on the already established scene of a tile, or of an entire level, right? The entire level's geometry is already determined, so then we can use that information to determine where the lights are placed, because everything that the lights can be placed on then becomes basically something that works, sometimes something that's satisfiable, because we already have this as satisfiable. So basically, yeah, this is how we go from answer set programming and some restrictions to an actual Metroidvania looking level. So that's it for my presentation. Thank you so much.